In this video, we're going to talk about temperature coefficient, and we're going to review a couple things. I got here first the solar cell equation, the energy level from the sun, the diode characteristic, and the series resistance. All right. Now, I stated before that this problem, because you got I here and here, and you want the output I current, this is a pain in the butt type of math problem. It's a mess. Now, there's a different way to approach this. We can use something called the temperature coefficient, and for power, the temperature coefficient ranges from 0.3 to 0.5% per degree C, relative to 25 degrees C, which is the standard test condition temperature. Now, sun power solar cells claim to have a 0.37% temperature coefficient. And I'm using that one because there was a fellow I've been following that uses that kind of solar panel. Now, the nominal operating temperature on the back of the label is much higher than the standard test condition. It usually varies between 45 to 50 degrees, depending on the manufacturer. And that's well above the STC temperature of 25 degrees. So we're going to calculate a delta T of the STC temperature of 25 minus the T nominal value. Now, this equation down here will give you the expected power out of a solar panel given the max power point at STC condition, the temperature coefficient, and if you notice it's 0.0037, that's how you turn a percent into a real number. Just divide by 100 times delta T. Now, I've seen a lot of papers or videos where they leave out this Pmax at the back here. They're taking a percentage of the Pmax parameter. Now, on my last video, part 5, I showed how to estimate the current energy now compared to the energy striking the panel at standard test conditions. Let's assume a T nominal value of 54 degrees C. Now, T nominal is an open circuit measurement as given on the back label, but if you take a infrared gun, you can estimate what that is. Pmax 190 watts. E now was 800. So the power, 190 minus a minus times 190, 0037. Delta T is minus 29 degrees, as configured up here, with a power ratio of 800 watts over standard test condition, 1000 watts. We're seeing that we're losing 20 watts of power just due to the temperature coefficient on a 190 watt panel. And then we multiply this by the 0.8. The panel output, given this temperature and this solar intensity, is only 135 watts per meter. 135 watts. Now, this is all pretty interesting. We got rid of the complicated math with the exponential and the diode equation. We kind of ignored this. And instead of calculating current, if V is 0 here, and here, all that goes away. So I short circuit is equal to I photon. And that's from the previous video. So, if you have a 190 watt panel and get 135 watts out of it, that's okay, because the radiation is lower and the temperature coefficient's eating your lunch. Bye-bye.